Let's get started. So welcome to the very final lecture of the class. I hope you're all surviving the last week and wrapping up your projects. So today we're going to be hearing about the future of NLP and deep learning. So Chris is still traveling, and today we're going to be having Kevin Clark, who's one of the PhD students in the lab, in the NLP lab. And he was also one of the head TAs for the class last year. So he's very familiar with the class as a whole. So take it away, Kevin.
OK. Thanks, Abby. Yeah, it's great to be back after being TA last year. I'm really excited today to be talking about the future of deep learning and NLP. Obviously, trying to forecast the future for deep learning or anything in that space is really difficult because the field is changing super quickly. So as one reference point, let's look at what did deep learning for NLP look like about 5 years ago. And really, a lot of ideas that are now considered to be pretty core techniques when we think of deep learning and NLP didn't even exist back then. So things you learned in this class, like seek-to-seek, attention mechanism, large-scale reading comprehension, even frameworks such as TensorFlow or PyTorch didn't exist. And the point I want to make with this is that because of this, it's really difficult to look into the future and say, OK, what are things going to be like? What I think we can do, though, is look at areas that right now are really sort of taking off. So areas in which there's been a lot of recent success, and kind of project from that those same areas will likely be important in the future. And in this talk, I'm going to be mostly focusing on one key idea, which is the idea of leveraging unlabeled examples when training our NLP systems. So I'll be talking a bit about doing that for machine translation, both in improving the quality of translation and even in doing translation in an unsupervised way. So that means you don't have paired sentences with their translations. You try to learn a translation model only from monolingual corpus. The second thing I'll be talking a little bit about is OpenAI's GPT-2, and in general, this phenomenon of really scaling up deep learning models. I know you saw a little bit of this in the lecture on contextual representation, but this will be a little bit more in depth. And I think these new developments in NLP have had some pretty big impacts in terms of more broadly kind of beyond even the technology we're using. And in particular, it's starting to raise more and more concerns about the social impact of NLP, both in what our models can do and also in kind of plans of where people are looking to apply these models. And I think that really has some risks associated with it in terms of security, also in terms of areas like bias. I'm also going to talk a bit about future areas of research. These are mostly research areas now that are, over the past year, have really kind of developed into promising areas, and I expect they will continue to be important in the future. OK, start with, I want to ask this question. Why has deep learning been so successful recently? I like this comic. Here there's a statistical learning person, and they've got some really complicated, well-motivated method for doing the task they care about. And then the neural net person just says, stack more layers. So the point I want to make here is that deep learning has not been successful recently because it's more theoretically motivated or it's more sophisticated than previous techniques. In fact, I would say that actually a lot of older statistical methods have more of a theoretical underpinning than some of the tricks we do in deep learning. Really, the thing that makes deep learning so successful in recent years has been its ability to scale. Right? So neural nets, as we increase the size of the data, as we increase the size of the models, they get really big boosts in accuracy in a way other approaches do not. And if you look to the 80s and 90s, there was actually plenty of research in neural nets going on, but it doesn't have the hype around it that it does now. And that seems likely to be because in the past, there wasn't the same resources in terms of computers, in terms of data. And only now, after we've reached sort of an inflection point where we can really take advantage of scale in our deep learning models, have we start to see it become a really successful paradigm for machine learning. If we look at big deep learning success stories, I think you can see kind of this idea play out, right? So here are 3 of what are arguably the most famous successes of deep learning, right? So there's image recognition, where before people used very highly engineered features to classify images, and now neural nets are much superior to those methods. Machine translation has really closed the gap between phrase-based systems and human quality translation. So this is widely used in things like Google Translate. The quality has actually gotten a lot better over the past 5 years. Another example that had a lot of hype around it is game playing. So there's been work on Atari games. There's been AlphaGo. More recently, there's been AlphaStar and OpenAI 5. If you look at all 3 of these cases, underlying these successes is really large amounts of data, right? So for ImageNet, for image recognition, there is the ImageNet dataset, which is 14 million images. Machine translation datasets often have millions of examples. For game playing, you can actually generate as much training data as you want, essentially, just by running your agent within the game over and over again. So if we looked at NLP, the story is quite a bit different for a lot of tasks, right? So if you look at even pretty core kind of popular tasks, so say reading comprehension in English, data sets like Squad are in the order of like 100,000 examples, which is considerably less than the millions or tens of millions of examples that these previous successes have benefited from. And that's, of course, only for English, right? There are thousands of other languages, and this is, I think, a problem with NLP data as it exists today. The vast majority of data is in English, when in reality, fewer than 10% of the world's population speak English as their first language. So these problems with small data sets are only compounded if you look at the full spectrum of languages that exist. So what do we do when we're limited by this data, but we want to take advantage of deep learning scale and train the biggest models we can? The popular solution that's especially had recent success is using unlabeled data. Because unlike labeled data is very easy to acquire for language. You can just go to the internet, you can go to books, you can get lots of text. Whereas labeled data usually requires, at the least, crowdsourcing examples. In some cases, you even require someone who's an expert in something like linguistics to annotate that data. OK, so this first part of the talk is going to be applying this idea of leveraging unlabeled data to improve our NLP models to the task of machine translation. So let's talk about machine translation data. It is true that there do exist quite large data sets for machine translation. Those data sets don't exist because NLP researchers have annotated text for the purpose of training their models, right? They exist because in various settings, translation is done just because it's useful. So for example, proceedings of the European Parliament, proceedings of the United Nations. Some news sites, they translate their articles into many languages. So really, the machine translation data we use to train our models are often more of byproducts of existing cases where translation is wanted, rather than kind of a full sampling of the sort of text we see in the world. So that means, number one, it's quite limited in domain, right? So it's not easy to find translated tweets unless you happen to work for Twitter. In addition to that, there's limitations in terms of the languages that are covered, right? So some languages, say European languages, there's a lot of translation data. For other languages, there's much less. So in these settings where we want to work on a different domain or we want to work with a low resource language, we're limited by labeled data. But what we can do is pretty easily find unlabeled data. So it's actually a pretty solved problem, maybe not 100%, but we can, with good accuracy, look at some text and decide what language it's in, train a classifier to do that. So this means it's really easy to find data in any language you care about, because you can just go on the web and essentially search for data in that language and acquire a large corpus of monolingual data. OK, I'm now going into the first approach I'm going to talk about on using unlabeled data to improve machine translation models. This technique is called pre-training, and it's really reminiscent of ideas like ELMO. The idea is to pre-train by doing language modeling. So if we have two languages we're interested in translating from one into the other, we'll collect large data sets for both of those languages. And then we can train two language models, one each, on that data. And then we can use those pre-trained language models as initialization for a machine translation system. So the encoder will get initialized with the weights of the language model trained on the source side language. The decoder will get initialized with weights trained on the target size language. And this will improve the performance of your model because during this pre-training, we hope that our language models will be learning useful information, such as the meaning of words or the kind of structure of the language they're processing. And this can, down the line, help the machine translation model when we fine-tune it. Let me pause here and ask if there are any questions. And just in general, feel free to ask questions throughout this talk. OK. So here is a plot showing some results of this pre-training technique. So this is English to German translation. The x-axis is how much training data, as in supervised training data, you provide these models. But of course, they also have large amounts of monolingual data for this pre-training step. And you can see that this works pretty well, right? So you get about 2 blue points increase in performance. So that's this red line above the blue line when doing this pre-training technique. And not too surprisingly, this gain is especially large when the amount of labeled data is small. There is a problem with pre-training, which I want to address, which is that in pre-training, you have these 2 separate language models, and there's never really any interaction between the two when you're running them on the unlabeled corpus. So here's a simple technique that tries to solve this problem. It's called self-training. The idea is, given a sentence from our monolingual corpus, so in this case, I travel to Belgium, it's an English sentence, we won't have a human-provided translation for this sentence, but what we can do is we can run our machine translation model, and we'll get a translation in the target language. Since this is from a machine learning model, it won't be perfect, but we can hope that maybe our model can still learn from this kind of noisy labeled example. Right? So we treat our original monolingual sentence and its machine-provided translation as though it were a human-provided translation and train our machine learning model as normal on this example. I think this seems pretty strange, actually, as a method when you first see it, because it seems really circular. Right? So if you look at this, the translation that the model is being trained to produce is actually exactly what it already produces to begin with, right? Because this translation came from our model in the first place. So actually, in practice, this is not a technique that's very widely used due to this problem, but it motivates another technique called back translation. And this technique is really a very popular solution to that problem. And it's a method that has had a lot of success in using unlabeled data for translation. So here's the approach. Rather than only having our translation system that goes from source language to target language, we're also going to train a model that goes from our target language to our source language. So in this case, if at the end of the day we want a French to English model, we're going to start by actually training an English to French model. And then we can do something that's a lot like self-labeling. So we take an English sentence, we run our English to French model and translate it. The difference to what we did before is that we're actually going to switch the source and target side. So now in this case, the French sentence is the source sequence. The target sequence is our original English sentence that came from our monolingual corpora. And now we're training the language, the machine translation system that goes the other direction, so that goes French to English. So why do we think this will work better? Number one, there's no longer this kind of circularity to the training, because what the model is being trained on is the output of a completely different model. Another thing that I think is pretty crucial here is that the translations the model is trained to produce, so the things that the decoder is actually learning to generate, are never bad translations, right? So if you look at this example, the target sequence for our French to English model, I travel to Belgium, that originally came from our monolingual corpus. So I think intuitively this makes sense, is that if we want to train a good translation model, it's probably OK to expose it to noisy inputs. So we expose it to the output of a system that's English to French. It might not be perfect. But what we don't want to do is expose it to poor target sequences, because then it won't learn how to generate in that language effectively. Any questions on back translation before I get to results? Sure.
Why do you say that data is not labeled? It's unlabeled?
So this is assuming we have a large corpus of unlabeled data, and we want to be using it to help our translation model. Does that make sense? Maybe you could clarify the question?
So does it mean that I don't know the correct translation for I travel to Belgium?
Yeah, that's right. So we have a big corpus of English, which includes the sentence, I traveled to Belgium, and we don't know the translations, but we'd still like to use this data. Yeah, another question?
To avoid the translation ended up collapsing some bad translation in the end.
Yeah, so that's a good question, is how do you avoid both the models, let's say, sort of blowing up and producing garbage, and then they're just feeding garbage to each other? The answer is that there is some amount of labeled data here as well. So on unlabeled data, you do this, but on labeled data, you do standard training, and that way, you make sure you kind of keep the models on track, because they still have to fit to the labeled data. Yeah, another question?
How do you schedule the training of the two models?
Yeah, that is a good question, and I think that's basically almost like a hyperparameter you can tweak. I think a pretty common thing to do is first train two models only on labeled data, then label. So then do back translation over a large corpus, and kind of repeat that process over and over again. So each iteration, you train on the labeled data, label some unlabeled data, and now you have more data to work with. But I think there'd be many kinds of scheduling that would be effective here. OK, another question?
Do you ever use this as a form of evaluation? Considering if you have a very good French to English model, you could try to look up, or to test if it's a good French to English model, you could try to look up the original source and see if it matches.
Yeah, I'm not quite sure. Are you suggesting going like English to French to English and seeing if, I see. Yeah, yeah, that's a really interesting idea. We're actually going to talk a little bit about this sort of, it's called cycle consistency, this idea later in this talk. OK, I'm going to move on to the results. So here's a method for using unlabeled data to improve translation. How well does it do? The answer is that the improvements are at least to me, they were surprisingly extremely good, right? So this is for English to German translation. This is from some work by Facebook. So they use 5 million labeled sentence pairs. But they also use 230 monolingual sentences, so sentences without translations. And you can see that compared to previous state-of-the-art, they get 6 blue points improvement, which, if you compare it to most previous research on machine translation, is a really big gain, right? So even something like the invention of the transformer, which most people would consider to be a really significant research development in NLP, that improved over prior work by about 2.5 blue points. And here, without doing any sort of fancy model design, just by using way more data, we get actually much larger improvements. OK, so an interesting question to think about is, suppose we only have our monolingual corpora. So we don't have any sentences that have been human translated. We just have sentences in 2 languages. So the scenario you can sort of imagine is, suppose an alien comes down and starts talking to you in its weird alien language, and it talks a lot. Would you eventually be able to translate what it's saying to English just by having a really large amount of data. So I'm going to start with a simpler task than full-on translating when you only have unlabeled sentences. Instead of doing sentence-to-sentence translation, let's start by only worrying about word-to-word translation. So the goal here is, given a word in one language, find its translation, but without using any labeled data. And the method we're going to use to try to solve this task is called cross-lingual embeddings. So the goal is to learn word vectors for words in both languages. And we'd like those word vectors to have all the nice properties you've already learned about word vectors having. But we also want word vectors for a particular language to be close to the word vector of its translation. So I'm not sure if it's visible in this figure, but this figure shows a large number of English and, I think, German words. And you can see that each English word has its corresponding German word nearby to it in its embedding space. So if we learn embeddings like this, then it's pretty easy to do word-to-word translation. We just pick an English word, we find the nearest German word in this joint embedding space, and that will give us a translation for the English word. Our key method or the key assumption that we're going to be using to solve this is that even though if you run word2vec twice, you'll get really different embeddings, the structure of that embedding space has a lot of regularity to it, and we can take advantage of that regularity to help find when an alignment between those embedding spaces. So to be kind of more concrete here, here is a picture of two sets of word embeddings. So in red, we have English words. In blue, we have Italian words. And although the vector spaces right now look very different to each other, you can see that they have a really similar structure, right? So you'd imagine distances are kind of similar, that the distance from cat and feline in the English embedding space should be pretty similar to the distance between gatto and felino in the Italian space. And this kind of motivates an algorithm for learning these cross-lingual embeddings. So here's the idea. What we're going to try to do is learn what's essentially a rotation such that we can transform our set of English embeddings so that they match up with our Italian embeddings. So mathematically what this means is we're going to learn a matrix W such that if we take, let's say, the word vector for cat in English and we multiply it by W, we end up with the vector for gatto in Spanish or Italian. And a detail here is that we're going to constrain W to be orthogonal. And what that means geometrically is just that W is only going to be doing a rotation to the vectors in X. It's not going to be doing some other weirder transformation. So this is our goal, is to learn this W. Next, I'm going to be talking about how actually do we learn this W. And there's actually a bunch of techniques for learning this W matrix. But here is one of them that I think is quite clever. It's called adversarial training. So it works as follows, is in addition to trying to learn this W matrix, we're also going to be trying to learn a model that is called a discriminator. And what it'll do is take a vector and it'll try to predict, is that vector originally an English word embedding or is it originally an Italian word embedding? In other words, if you think about the diagram, what we're asking our discriminator to do is it's given one of these points and it's trying to predict, is it basically a red point, so an English word originally, or is it a blue point? So if we have no W matrix, then this is a really easy task for the discriminator because the word embeddings for English and Italian are clearly separated. However, if we learn a W matrix that succeeds in aligning all these embeddings on top of each other, then our discriminator will never do a good job, right? We can imagine it'll never really do better than 50% because given a vector for, say, cat, it won't know, is that the vector for cat that's been transformed by W, or is it actually the vector for gatto? Because in this case, those two vectors are aligned, so they're on top of each other. During training, you first you alternate between training the discriminator a little bit, which means making sure it's as good as possible at distinguishing the English from Italian words. And then you train the W, and the goal for training W is to essentially confuse the discriminator as much as possible. So you want to have a situation where you can't, with this machine learning model, figure out if a word embedding actually was originally from English or if it's an Italian word vector. And so at the end of the day, you have vectors that are kind of aligned with each other. Any questions about this approach? Okay. Here, there's a link to a paper with more details. There's actually kind of a range of other tricks you can do, but this is kind of a key idea. Okay, so that was doing word-to-word unsupervised translation. How do we do full sentence-to-sentence translation? So we're going to use a standard sort of seek-to-seek model without even an attention mechanism. There's one change to the standard seek-to-seek model going on here, which is that we're going to use the same encoder and decoder regardless of the input and output languages. So you can see in this example, we could give the encoder an English sentence. We could also give it a French sentence, and it'll have these cross-lingual embeddings, so it'll have vector representations for English words and French words, which means it can handle sort of any input. For the decoder, we need to give it some information about what language is it supposed to generate in. Is it going to generate in French or English? So the way that is done is by feeding in a special token, which here is FR in brackets to represent French, that tells the model, OK, you should generate in French now. Here in this figure, it's only French, but you could imagine also feeding this model English in brackets, and then that'll tell it to generate in English. And one thing you can see is that you could use this sort of model to go from English to French. You could also use this model as an autoencoder, right? So at the bottom, it's taking in a French sentence as input, and it's just generating French as output, which here means just reproducing the original input sequence. So just a small change to standard seek-to-seek. Here's how we're going to train the seek-to-seek model. There's going to be two training objectives. And I'll explain sort of why they're present in this model in just a few slides. For now, let's just say what they are. So the first one is called a denoising autoencoder. What we're going to train our model to do in this case is take a sentence. So, and here it's going to be an English sentence, but it could also be a French sentence. We're going to scramble up the words a little bit. And then we're going to ask the model to denoise that sentence, which in other words means regenerating what the sentence actually was before it was scrambled. And maybe one idea of why this would be a useful training objective is that since we have an encoder-decoder without attention, the encoder is converting the entirety of the source sentence into a single vector. What an autoencoder does is ensure that that vector contains all the information about the sentence such that we are able to recover what the original sentence was from the vector produced by the encoder. So that was objective one. Training objective two is now we're actually going to be trying to do translation. But as before, we're going to be using this back translation idea. So remember, we only have unlabeled sentences. We don't have any human-provided translations. But what we can still do is given a, let's say an English sentence, or let's say a French sentence, given a French sentence, we can translate it to English using our model in its current state. And then we can ask that model to translate from English, or translate that English back into French. So what you can imagine is in this setting, the input sequence is going to be somewhat messed up because it's the output of our imperfect machine learning model. So here the input sequence is just I am student. A word has been dropped. But we're now going to train it to, even with this kind of bad input, to reproduce the original French sentence from our corpus of monolingual French text. Let me pause here actually and ask for questions. Sure.
Just a quick thing. What if the reason you had this orthogonality constraint for your word to word embedding, is it to avoid overfitting? Have you tried to take that off and to see what you guys results?
Yeah, that's a good question. So this is going back to earlier when there was word-word translation. Why would we constrain that W matrix to be orthogonal? Essentially, that's right. It's to avoid overfitting, and in particular, it's making this assumption that our embedding spaces are so similar that there's actually just a rotation that distinguishes our word vectors in English versus our word vectors in Italian. I think there have been results that don't include that orthogonality constraint, and I think it slightly hurts performance to not have that in there. Okay. So continuing with unsupervised machine translation, I gave a training method. I didn't quite explain why it would work. So here is some more intuition for this idea. So remember, we're going to initialize our machine translation model with these cross-lingual embeddings, which mean the English and French word should look close to identically. We're also using the shared encoder. So that means if you think about it, at the top we have just a auto-encoding objective, and we can certainly believe that our model can learn this. It's a pretty simple task. Now imagine we're giving our model a French sentence as input instead. Since the embeddings are going to look pretty similar, and since the encoder is the same, it's pretty likely that the model's representation of this French sentence should actually be very similar to the representation of the English sentence. So when this representation is passed into the decoder, we can hope that we'll get the same output as before. So here's like sort of as a starting point, we can hope that our model already is able to have some translation capability. Another way of thinking about this is that what we really want our model to do is to be able to encode a sentence such that that representation is sort of a universal kind of interlingua, so a universal universal representation of that sentence that doesn't that's not specific to the language. And so here's kind of a picture that's trying to get at this. So our autoencoder and our back translation example, here the target sequence is the same. So what that essentially means is that the vectors for the English sentence and the French sentence are going to be trained to be the same, right? Because if they were different, our decoder would be generating different outputs on these two examples. So this is just another sort of intuition, is that what our model is trying to learn here is kind of a way of encoding the information of a sentence in a vector, but in a way that is language agnostic. Any more questions about unsupervised machine translation? Okay, so going on to results of this approach. Here, the horizontal lines are the results of an unsupervised machine translation model. The lines that go up are for a supervised machine translation model as we give it more and more data. Right, so unsurprisingly, given a large amount of supervised data, the supervised machine translation models work much better than the unsupervised machine translation model. But the unsupervised machine translation model actually still does quite well. So if you see it around 10,000 to 100,000 training examples, it actually does just as well or better than supervised translation. And I think that's a really promising result, because if you think of low resource settings where there isn't much labeled examples, then suddenly becomes really nice that you can perform this well without even needing to use a training set. Another thing kind of fun you can do with a unsupervised machine translation model is attribute transfer. So basically, you can take collections of text that split by any attribute you want. So for example, you could go on Twitter, look at hashtags to decide which tweets are annoyed and which tweets are relaxed. And then you can treat those two corpora as text as though they were two different languages. And you can train an unsupervised machine translation model to convert from one to the other. And you can see these examples. The model actually does a pretty good job of sort of minimally changing the sentence, kind of preserving a lot of that sentence's original semantics, such that the target attribute is changed. I also want to throw a little bit of cold water on this idea. So I do think it's really exciting and almost kind of mind-blowing that you can do this translation without labeled data. Certainly, right, it's really hard to imagine someone giving me a bunch of books in Italian and say, okay, learn Italian, without teaching you how to specifically do the translation. But even though these methods show promise, mostly they have shown promise on languages that are quite closely related. So those previous results, those were all some combination of English to French or English to German or so on, and those languages are quite similar. So if you look at a different language pair, let's say English to Turkish, where the linguistics in those two languages are quite different, these methods do still work to some extent. So they get around 5 blue points, let's say, but they don't work nearly as well as they do in the other settings, right? So there's still a huge gap to purely supervised learning. Right, so we're probably not, quite at this stage where an alien could come down and it's sort of no problem. Let's use our unsupervised machine translation system. But I still think it's pretty exciting progress. Yeah, question?
So what you're saying is that the genealogy of the language might lead it to superimpose worse, right? Because my original thought was that if you took, for example, like Latin, which doesn't have a word for, like the modern concept of a car, I thought that would do more poorly. But basically what I'm asking is, do you think English maps better to Latin because they're both related and worse to Turkish, or is it the other way around?
I would expect English to map quite a lot better to Latin. And I think part of the issue here is that the difficulty in translation, I think, is not really at the word level. So I mean, that certainly is an issue that words exist in one language that don't exist in another. But I think actually more substantial differences between language is at the level of like syntax or semantics, right? How ideas are expressed. So I think I would expect Latin to have relatively similar syntax to English compared to, say, Turkish. And I imagine that is probably the bigger obstacle for unsupervised machine translation models. I'm going to really quickly go into this last recent research paper, which is basically taking BERT, which you've learned about, correct? Yes? OK, and making it cross-lingual. So here's what regular BERT is, right? We have a sequence of sentences in English. We're going to mask out some of the words. And we're going to ask BERT, which is our transformer model, to essentially fill in the blanks and predict what were the words that were dropped out. What actually has already been done by Google is training a multilingual BERT. So what they did essentially is concatenate a whole bunch of corpora in different languages and then train one model using this masked LM objective on all of that text at once. And that's a publicly released model. The new kind of extension to this that has recently been proposed by Facebook is to actually combine this masked LM training objective with translation. So what they do is sometimes give this model in this case, a sequence in English and a sequence in French, drop out some of the words, and just as before, ask the model to fill it in. And the motivation here is that this will much better cause the model to understand the relation between these two languages, because if you're trying to fill in an English word that's been dropped, the best way to do it, if you have a translation, is look at the French side and try to find that word. Hopefully that one hasn't been dropped as well, and then you can much more easily fill in the blank. And this actually leads to very substantial improvements in unsupervised machine translation. So just like BERT is used for other tasks in NLP, they basically take this cross-lingual BERT, they use it as initialization for an unsupervised machine translation system, and they get really large gains on the order of 10 blue points, such that the gap between unsupervised machine translation and the current supervised state of the art is much smaller. This is a pretty recent idea, but I think it also shows promise in really improving the quality of translation through using unlabeled data. Although I guess in this case of BERT, they are using label translation data as well. Any questions about this? Okay. So that is all I'm going to say about using unlabeled data for translation. The next part of this talk is about what happens if we really scale up these unsupervised language models. So in particular, I'm going to talk about GPT-2, which is a new model by OpenAI that's essentially a really giant language model, and I think it has some interesting implications. So first of all, here's just the sizes of a bunch of different NLP models, and maybe a couple years ago, the standard sort of LSTM medium-sized model was on the order of about 10 million parameters, where a parameter is just a single weight, let's say, in the neural net. Elmo and GPT, so the original OpenAI paper before they did this GPT-2, and we're about 10 times bigger than that. GPT-2 is about another order of magnitude bigger. One kind of interesting comparison point here is that GPT-2, which is 1.5 billion parameters, actually has more parameters than a honeybee brain has synapses. So that sounds kind of impressive, right? Honeybees are not the smartest of animals, but they can still fly around and find nectar or whatever. But of course, this isn't really an apples-to-apples comparison, right? So a synapse and a weight in a neural net are really quite different. But I just think it's one kind of interesting milestone, let's say, in terms of model size that has been surpassed. One thing to point out here is that this increasing scaling of deep learning is really a general trend in all of machine learning, so beyond NLP. So this plot is showing time on the x-axis, and the y-axis is log-scaled the amount of petaflops used to train this model. So what this means is that the trend, at least currently, is that there's exponential growth in how much compute power we're throwing at our machine learning models. I guess it is kind of unclear, will exponential growth continue? But certainly there's rapid growth in the size of our models. And it's leading to some really amazing results, right? So here are results not from language, but for vision. This is a generative adversarial network that's been trained on a lot of data, and it's been trained at really large scale. So it's a big model kind of in between the size of Elmo and BERT, let's say. And these photos here are actually productions of the model. So those aren't real photos. Those are things the model has just kind of hallucinated out of thin air. And at least to me, they look essentially photorealistic. There's also a website that is fun to look at if you're interested, which is thispersondoesnotexist.com. So if you go there, you'll see a very convincing photo of a person, but it's not a real photo. It's, again, like a hallucinated image produced by a GAN. We're also seeing really huge models being used for image recognition. So this is recent work by Google, where they trained an ImageNet model with 500 million parameters. So that's bigger than BERT, but not as big as GPT-2. This plot here is showing log-scaled number of parameters on the x-axis, and then accuracy at ImageNet on the y-axis. And sort of unsurprisingly, bigger models perform better. And there seems to actually be a pretty consistent trend here, which is accuracy is increasing with the log of the model size. I want to go into a little bit more detail. How is it possible that we can scale up models and train models at such a large extent? One answer is just better hardware. And in particular, there's a growing number of companies that are developing hardware specifically for deep learning. So these are even more kind of constrained in the kind of operations they can do than a GPU, but they do those operations even faster. So Google's tensor processing units is one example. There are actually a bunch of other companies working on this idea. The other way to scale up models is by taking advantage of parallelism. And there's two kinds of parallelism that I want to talk about very briefly. So one is data parallelism. In this case, each of your, let's say, GPUs will have a copy of the model. And what you essentially do is split the mini batch that you're training on across these different models. So if you have, let's say, 16 GPUs and each of them see a batch size of 32, you can aggregate the gradients of these 16, if you do backprop on these 16 GPUs, and you end up with effectively a batch size of 512. So this allows you to train models much faster. The other kind of parallelism that's growing in importance is model parallelism. Eventually, models get so big that they can't even fit on a single GPU, and they can't even do a batch size of 1. In this case, you actually need to split up the model across multiple compute units. That's what's done for models kind of the size of let's say, GPT-2. There are new frameworks such as Mesh TensorFlow, which are basically designed to make this sort of model parallelism easier. OK, so on to GPT-2. I know you already saw this a little bit in the contextualized embeddings lecture, but I'm going to go into some more depth here. So essentially, it's a really large transformer language model. So there's nothing really kind of novel here in terms of new training algorithms or in terms of the loss function or anything like that. The thing that makes it different from prior work is that it's just really, really big. It's trained on a correspondingly huge amount of text, so it's trained on 40 gigabytes, and that's roughly 10 times larger than previous language models have been trained on. When you have that size of data set, the only way to get that much text is essentially to go to the web. So one thing OpenAI put quite a bit of effort into when they're developing this network was to ensure that that text was pretty high quality. And they did that in a kind of interesting way. They looked at Reddit, which is this website where people can vote on links. And then they said, if a link has a lot of votes, then it's probably sort of a decent link. There's probably reasonable text there for a model to learn. OK, so if we have this super huge language model like GPT-2, there's a question of what can you actually do with it? Well, obviously, if you have a language model, you can do language modeling with it. But one thing kind of interesting is that you can run this language model on existing benchmarks for language modeling. And it gets state-of-the-art perplexity on these benchmarks, even though it never sees the training data for these benchmarks, right? So normally, if you want to, say, evaluate a language model on the Penn tree bank, you first train on the Penn tree bank, and then you evaluate on this held-out set. In this case, GPT-2, just by virtue of having seen so much text and being such a large model, outperforms all these other prior works, even though it's not seeing that data on a bunch of different language modeling benchmarks. But there's a bunch of other interesting experiments that OpenAI ran with this language modeling, and these were based on zero-shot learning. So zero-shot learning just means trying to do a task without ever training on it. And the way you can do this with a language model is by designing a prompt you feed into the language model, and then have it just generate from there, and hopefully it generates something relevant to the task you're trying to solve. So for example, for reading comprehension, what you can do is take the context paragraph, concatenate the question to it, and then add a colon, which is a way, I guess, of telling the model, OK, you should be producing an answer to this question, and then just have it generate text. And perhaps it'll generate something that is actually answering the question and is paying attention to the context. And similarly for summarization, you can do the article, then TLDR, and perhaps the model will produce a summary. You can even do translation, where you give the model a list of known English to French translations. So you sort of prime it to tell it that it should be doing translation. And then you give it the source sequence equals blank and have it just run. And perhaps it'll generate the sequence in the target language. OK, so here are what the results look like. For all of these, the x-axis is log-scaled model size. The y-axis is accuracy. And the dotted lines basically correspond to existing works on these tasks. So for most of these tasks, GPT-2 is quite a bit below existing systems. But there's, of course, this big difference, right? Existing systems are trained specifically to do whatever task they're being evaluated on, where GPT-2 is only trained to do language modeling. And as it learns language modeling, it's sort of picking up on these other tasks. So for example, it does English to French machine translation, not as well as standard unsupervised machine translation, which is those dotted lines. But it still does quite well. And one thing kind of interesting is the trend line, right? For almost all of these tasks, performance is getting much better as the model increases in size. I think a particularly interesting one of these tasks is machine translation, right? So the question is, how can it be doing machine translation when all we're giving it is a bunch of web pages, and those web pages are almost all in English? And yet somehow it sort of magically picks up a little bit of machine translation, right? So it's not a great model, but it can still do a decent job in some cases. And the answer is that if you look at this giant corpus of English, occasionally within that corpus, you see examples of translations, right? So you see a French idiom and its translation, or a quote from someone who's French, and then the translation in English. And kind of amazingly, I think, this big model sees enough of these examples that it actually starts to learn how to generate French, even though that wasn't really sort of an intended part of its training. Another interesting thing to dig a bit more into is its ability to do question answering. A simple baseline for question answering gets about 1% accuracy. GPT-2 barely does better at 4% accuracy. So this isn't like, super amazing, we solved question answering. But it's still pretty interesting in that if you look at answers the model is most confident about, you can see that it sort of has learned some facts about the world, right? So it's learned that Charles Darwin wrote Origin of Species. Normally in the history of NLP, if you want to get kind of world knowledge into an NLP system, you'd need something like a big database of facts. And even though this is still kind of very early stages and that there's still a huge gap between 4% accuracy and the 70% or so that state-of-the-art open domain question answering systems can do, it still can pick up some world knowledge just by reading a lot of text without kind of explicitly having that knowledge put into the model. Any questions, by the way, on GPT-2 so far? OK. So one question that's interesting to think about is what happens if our models get even bigger? So here I've done the very scientific thing of drawing some lines in PowerPoint and seeing where they meet up. And you can see that if the trend holds at about 1 trillion parameters, we get to human level reading comprehension performance. So if that's true, it would be really astonishing. I actually do expect that a 1 trillion parameter model would be attainable in, 10 years or so. But of course, right, the trend isn't clear. So if you look at summarization, for example, it seems like performance is already topped out. So I think this will be a really interesting thing kind of going forward, looking at the future of NLP, is how this scaling will change the way NLP is approached. The other interesting thing about GPT-2 was its reaction from the media and also from other researchers. And the real cause of a lot of the controversy about it was this statement from OpenAI. They said that we're not going to release our full language model because it's too dangerous. Our language model is too good. So the media really enjoyed this and said that machine learning is going to break the internet. There's also some pretty interesting reaction from researchers, right? So there's some kind of tongue-in-cheek responses here, right? I trained a model on MNIST. Is it too dangerous for me to release it? And similarly, we've done really great work, but we can't release it. It's too dangerous. So you're just going to have to trust us on this. Looking at more kind of reasoned debate about this issue, you still see articles arguing both sides. So these are two articles from The Gradient, which is a sort of machine learning newsletter. And they're arguing precisely opposite sides of this issue. Should it be released or not? So I guess I can briefly go over a few arguments for or against. There's kind of a lot of debate about this, and I don't want to go too deep into a controversial issue. But here's a long list of kind of things people have said about this, right? So here's why you should release. One complaint is that, is this model really that special? There's nothing new going on here. It's just 10 times bigger than previous models. And there's also some arguments that even if this one isn't released, in 5 years, everybody can train a model this good. And actually, if you look at image recognition or look at images and speech data, it already is possible to synthesize highly convincing fake images and fake speech. So kind of what makes this thing different from those other systems. And speaking of other systems, right, Photoshop has existed for a long time, so we can already convincingly fake images. People have just learned to adjust and learn that you shouldn't always trust what's in an image because it may have been altered in some way. On the other hand, you could say, okay, Photoshop exists, but you can't sort of scale up Photoshop and start mass producing fake content the way you can with this sort of model. And they point to the danger of fake news, fake reviews, in general, just astroturfing, which means basically creating fake user content that's supporting a view you want other people to hold. This is actually something that's already done pretty widely by companies and governments. So there's a lot of evidence for this. But they're, of course, hiring people to write all these comments on news articles, let's say. And we don't want to make their job any easier by producing a machine that could potentially do this. So I'm not really going to take a side here. There's still a lot of debate about this. I think the main takeaway here is that as a community, people in machine learning and NLP don't really have a handle on this, right? We're sort of caught by surprise by OpenAI's decision here. And that means that there really is some figuring out that needs to be done on what exactly is responsible to release publicly, what kind of research problems should we be working on, and so on. So yeah, any questions about this reaction or this debate in general? Okay. I think something arising from this debate is the question of should really the ML people be the people making these sort of decisions, or is there a need for more interdisciplinary science where we look at experts in, say, computer security, people from social sciences, people who are experts in ethics to look at these decisions. Right, so GPT-2 is definitely one example of where suddenly it seems like our NLP technology has a lot of pitfalls, right, where they could be used in a malicious way or they could cause damage. And I think this trend is only going to increase. If you look at kind of areas of NLP that people are working on, increasingly people are working on really high stakes applications of NLP. And those often have really big ramifications, especially if you think from the angle of bias and fairness. So let's go over a couple examples of this. some areas where this is happening is people are looking at NLP to look at judicial decisions. So for example, should this person get bail or not? For hiring decisions, right? So you look at someone's resume, you run NLP on it, and then you make a decision automatically, should we throw out this resume or not? So do some sort of screening, grading tests. If you take the GRE, your test will be graded by a machine. A person will also look at it, but nevertheless, that's a sometimes very impactful part of your life when it's a test that affects your acceptance into a school, let's say. So I think there are some good sides of using machine learning in these kinds of contexts. So one is that we can pretty quickly evaluate a machine learning system and search out, does it have some kind of bias, just by running it on a bunch of data and seeing what it does. And also, perhaps even more importantly, we can fix this kind of problem if it arises, right? So it's probably easier to fix a machine learning system that screens resumes than it is to fix having 5,000 executives that are slightly sexist or something, right? So in this way, there is a sort of positive angle on using machine learning in these high stakes decisions. On the other hand, it's been pretty well known, and I know you had a lecture on bias and fairness, that machine learning often reflects bias in a data set. It can even amplify bias in the data set. And there's concern of kind of a feedback loop where a biased algorithm actually will lead to the creation of more biased data, in which case these problems will only compound and get worse. So for all of the high impact decisions I had listed on that slide, there are examples where things have gone awry, right? So Amazon had some AI that was working as a recruiting tool and it turned out to be sexist. There's been some kind of early pilots of using AI in the justice system, and those also have had, in some cases, really bad results. If you look at automatic essay grading, it's not really a great NLP system, right? So here's an example excerpt of an essay that a automatic grading system used by the GRE test gives a very high score. But really, it's just kind of a salad of big fancy words, and that's enough to convince the model that this is a great essay. The last area that I want to talk about where you can see there's really some risks and some pitfalls with using NLP technology is chatbots. So I think chatbots do have a side where they can be very beneficial. Woebot is one example. It's this company that has this chatbot you can talk to if you're not feeling too great, and it'll try to, I don't know, cheer you up. So that could be a really nice piece of technology that helps people. But on the other hand, there's some big risks. So one example is Microsoft Research had a chatbot trained on tweets, and it started quickly saying racist things and had to be pulled. So I think all of this highlights that as NLP is becoming more effective, people are seeing opportunities to use it in increasingly high stakes decisions. And although there's some appeal to that, there's also a lot of risk. Any more questions on this sort of social impact of NLP? Okay. Last part of this lecture is looking more at future research, right? And in particular, I think a lot of the current research trends are kind of reactions to BERT, right? So the question is, what did BERT solve, and what do we work on next? So here are results on the GLUE benchmark. That is a compendium of 10 natural language understanding tasks, and you get an average score across those 10 tasks. The two rightmost models are are just supervised trained machine learning systems, right? So we have bag of vectors. We instead use our fancy neural net architecture of BiOSTM plus attention, and we get about 5 points. But the gains from BERT really dwarf that difference, right? So BERT improves results by about 17 points, and we end up being actually quite close to human performance on these tasks. So one sort of implication of this that people are wondering about is this kind of the death of architecture engineering? So I'm sure all of you who have worked on the default final project have seen a whole bunch of fancy pictures showing different architectures for solving squad. There are a lot of papers. They all propose some kind of attention mechanism or something like that. Right, with BERT, it's sort of, you don't need to do any of that, right? You just train a transformer and you give it enough data, and actually you're doing great on squad. You know, maybe these architectural enhancements are not necessarily the key thing that'll drive progress in improving results on these tasks. Right, so if you look at this at the perspective of a researcher, you can think a researcher will say, okay, I could spend 6 months designing a fancy new architecture for squad, and if I do a good job, maybe I'll improve results by one F1 point. But in the case of BERT, increasing the size of their model 3x, which is the difference between, they have like a base size model and a large model, that improved results by 5 F1 points. So that does seem to suggest we need to sort of reprioritize which avenues of research we pursue, because this architecture engineering isn't providing kind of gains for its time investment the way leveraging unlabeled data is. So now if you look at the squad leaderboard, I think at least the top 20 entrants are all BERT plus something. One other issue I think BERT has raised is that we need harder tasks, right? BERT has almost solved squad if you define it by getting close to human performance. So there's been a growth in new data sets that are more challenging. And there are a couple ways in which they can be more challenging. So one is doing reading comprehension on longer documents or doing it across more than one document. One area is looking at coming up with harder questions that require multi-hop reasoning. So that essentially means you have to string together multiple supporting facts from different places to produce the correct answer. And another area, situating question answering within a dialogue. There's also been a kind of small detail with the construction of reading comprehension data sets that has actually really affected the difficulty of the task. And that is whether, when you create these data sets, is the person who writes questions about a passage, can they see that passage or not? So of course, it's much easier to come up with a question that when you see the passage, and if you come up with a question without seeing the passage, you may not even have an answerable question. But the problem with looking at the passage is that, first of all, it's not realistic, right? So if I'm asking a question, I'm not going to have usually the paragraph that answers that question sitting in front of me. On top of that, it really encourages easy questions, right? So if you're a mechanical Turker and you're paid to write as many questions as possible, and then you see an article that says, I don't know, Abraham Lincoln was the 16th president of the United States. What are you going to write as your question? You're going to write, who was the 16th president of the United States? You're not going to write something more interesting that's harder to answer. So this is one way in which crowdsourced data sets have changed. People are now making sure questions are sort of independent of the contexts. So I'm going to briefly go over a couple new data sets in this line. So one is called QAC, which stands for Question Answering in Context. In this data set, there is a teacher and a student. The teacher sees a Wikipedia article. The student wants to learn about this Wikipedia article. And the goal is to train a machine learning model that asks as the teacher. So you can imagine maybe in the future, this sort of technology would be useful for education, for kind of adding some automation. One thing that makes this task difficult is that questions depend on the entire history of the conversation. So for example, if you look on the left here, the example dialogue, the third question is, was he the star? Clearly, you can't answer that question unless you look back earlier in the dialogue and realize that the subject of this conversation is Daffy Duck. And sort of because this data set is more challenging, you can see there's a much bigger gap to human performance, right? So if you train some BERT with some extensions, the results are still like 15 F1 points worse than human performance. Here's one other data set called HotPot QA. it is designed instead for multi-hop reasoning. So essentially, in order to answer a question, you have to look at multiple documents. You have to look at different facts from those documents and perform some inference to get what the correct answer is. So I think this is a much harder task. And again, there's a much bigger gap between human performance. Any questions on new data sets, harder tasks for NLP? Okay. I'm going to kind of rapid fire go through a couple more areas in the last minutes of this talk. So multitask learning, I think, is really growing in importance. Of course, you've had a whole lecture on this, right? So I'm not going to spend too much time on it. But maybe one point of interest is that if you look at performance on this GLUE benchmark, so this benchmark for natural language understanding, all the top couple results that are now actually surpassing BERT in performance is taking BERT and training it in a multitask way. I think another interesting motivation for multitask learning is that if you are training BERT, you have a really, really large model. And one way to make more efficient use of that model is training it to do many things at once. Another area that's definitely important, and I think will be important going in the future, is dealing with low resource settings. And here I'm using a really broad definition of resources, right? So that could mean compute power. BERT is great, but it also takes huge amounts of compute to run it. So it's not realistic to say if you're building, let's say, an app for a mobile device, that you could run a model the size of BERT. As I already went into earlier in this talk, low resource languages is an area that I think is pretty underrepresented in NLP research right now because most data sets are in English. But I do think, right, there's a really large number of people that in order to benefit from NLP technology, we'll need to have technologies that work well in a lot of different languages, especially those without much training data. And speaking of low amounts of training data, I think in general this is an interesting area of research. Within machine learning, actually, people are working a lot on this as well. So a term often used is few-shot learning. And that essentially means being able to train a machine learning model that only sees, let's say, 5 or 10 examples. One motivation there is, I think, a clear distinction between how our existing machine learning systems learn and how humans learn is that humans can generalize very quickly from 5 or so examples. If you're training a neural net, you normally need thousands of examples or perhaps even tens of thousands, hundreds of thousands of examples to get something that works. So I also see this being a pretty important area in the future. The last area where I want to go in a little bit more depth is interpreting and understanding models. So really there's 2 aspects of this. One is if I have a machine learning model and it makes a prediction, I would like to be able to know why did it make that prediction. So get some rationale, get some explanation. That would especially be important in an area like healthcare, right? So if you're a doctor and you're making a decision, it's probably not good enough for your machine learning model to say patient has disease X. You really want it to say patient has disease X for these reasons, because then you as a doctor can double check and try to validate the machine's thinking, I guess, to come up with that diagnosis. The other area of interpreting understanding models is more of a scientific question, right? Is we know things like BERT work really well. We want to know why do they work well? What aspects of language do they model? What things don't they model? And that might lead to ideas of improving those models. So here is a couple slides on the main approach for answering these sort of scientific questions. What does a machine learning model learn? What you do is you have a model, so let's say it's BERT. It takes as input a sequence of words. It produces as output a sequence of vectors. we want to ask, does it know, for example, the part-of-speech of words? So it does, in its vector representations, does that capture something about syntax? And a simple way of asking this question is train another classifier on top of BERT that's trained to do, let's say, part-of-speech tagging. But we only backprop into that diagnostic classifier itself. So in other words, we're treating the output of BERT, that sequence of vectors, as a fixed input, and we're sort of probing those vectors to see, do they contain information about part of speech that this second diagnostic classifier on top can decode to get the correct labels. There's kind of quite a few concerns here. One concern is if you make your diagnostic classifier too complicated, it can just solve the task all on itself, and it can basically ignore whatever representations were produced by BERT. So the kind of standard thing right now is to use a single softmax layer on top of BERT to do these decisions. And there's been a whole bunch of tasks proposed for evaluating essentially the linguistic knowledge of these models. So you could do part-of-speech tagging. You could do more semantic tasks like relation extraction or something like coreference. And this is a pretty active area of work. Here is just one plot showing some of the results of this approach. So here what we're doing is we're adding diagnostic classifiers to different layers of BERT. And we are seeing which layers of BERT are more useful for particular tasks. Something kind of interesting comes out of this, which is that the different layers of BERT seem to be corresponding fairly well with notions of different layers of linguistics. Dependency parsing, which is a syntactic task, it's considered sort of a medium level task in understanding a sentence. The medium layers of BERT, so layers kind of 6 through 8 or something, are the ones best at dependency parsing. If you have a very semantic task like sentiment analysis, where you're trying to learn some kind of semantic property of the whole sentence, then the very last layers of BERT are the one that seem to encode the most information about this phenomena. Okay, so this is almost it for the talk. I just have one slide here of NLP not in kind of the academic researchy context, which I've already been talking a lot about, but NLP in industry, and really there's rapid progress there. And I want to point to 2 areas where I think there's especially a large interest in using NLP technology. One is dialogue. So for things like chatbots, right, there's the Alexa Prize, where they're actually investing a lot of money in having groups figure out how to improve chit-chat dialogue. There's also, I think, a lot of potential for customer service, right? So improving basically automated systems that'll, book you a flight or help you cancel a subscription or anything like that. And similarly, there's a lot of potential in healthcare. One is understanding the records of someone who is sick and to help with diagnoses. I think another equally important area is actually parsing biomedical papers. The number of biomedical papers that are being written is really insane. It's way larger than the number of computer science papers that are being written. Often, if you are a doctor or if you're a researcher in medicine, you might want to look up something very specific, right? You might want to know what is the effect of this particular drug on this particular gene or a cell with this particular gene. There's no good way right now of searching through hundreds of thousands of papers to find if someone has done this experiment and have results for this particular combination of things. So automated reading of all this biomedical literature could have a lot of value. Okay, to conclude, there's been rapid progress in the last 5 years due to deep learning in NLP. In the last year, we've seen another really kind of a dramatic increase in the capability of our systems thanks to using unlabeled data. So that's methods like BERT. The other kind of thing that's, I think, important to think about is that NLP systems are starting to be at a place where they can have big social impact. So that makes some issues like bias and security very important. Thank you. Good luck finishing all your projects.